Okay, so in this video, what we're going to look at is an introduction of the idea of a definite integral. And it's going to pick up right where we left off in the last video. So in the last video, we were using basically the idea of a summation of a bunch of little rectangles to try to find the area under a curve. So we had an area under a curve that we were interested in finding. We chopped that area up into approximately rectangles. We found the areas of each of those rectangles and added them all up to find the total area under the curve. When we took the limit so that we increased the number of rectangles, so we're using more and more rectangles, and the width of those rectangles is going to 0, we got better and better results. And so let me give you a sense of a picture of what that's going to look like, and we can come back. So basically, this is from last time. Recall that what we're interested in doing is dealing with something that looks like this. We've got some function doing whatever it happens to do. So let's call it f of x, y equals f of x. Right here, we've got a starting point A, an ending point B. This is my x-axis, this is my y-axis, and I want the area of this region. The way that we found that area was by chopping up this large area into a bunch of rectangles. So I put a rectangle here, put a rectangle here, put a rectangle here, and so on, all the way to the end. And we pick some point where we're going to basically pick the heights of all of these things. Let's do it all the way to the end. Hopefully we make our rectangles equal widths. Mine didn't quite work out that way, but let's just pretend it did. So let me cheat and say that's actually where this interval ends, so that my rectangles are at least roughly the same size. Come on. So in this video, I want to take a look at the definite integral. I want to define what this thing is. We've been talking about integrals already without actually having a concrete definition of what it means. So we're going to define the definite integral in the context of the stuff we were working on last time. Last time, we were trying to find the area under a curve. We found that area under a curve by taking the region we were interested in and chopping it up into a bunch of pieces. And each of those little pieces was approximately a rectangle. We could figure out the area of the rectangle by just multiplying the height of the rectangle times the width of the rectangle, and that would give us the area of each little rectangle. We would do that for all the little rectangles that we'd built up this big region out of, and we would have an approximate area for the whole region. So let me give you a quick picture of what that looks like, and we'll refer back to this picture in just a minute when we define the concept of a definite integral. So here are my axes, here's my x-axis and my y-axis, and here's some function doing whatever it happens to do. Y equals f of x. And I'm interested in finding the area under the curve y equals f of x between A and B. So here's where it starts, here's where it ends. I'm interested in finding this area. So that's what we want. We found that area again by chopping this thing up into pieces. So let's say if I ballpark it here, we can get close to an even number. Let's do 8 little rectangles here. Looks pretty close. These are fairly even. And so the heights of these rectangles, again, they're actual rectangles, so they're sort of squared out at some point. They look something like this. And we would get an approximation for the area under the curve by looking at all of those little tiny rectangles. So this is what I want to talk about, the area under that curve. I'm going to define the definite integral in the context of this particular example. So let's start with the definition, and we'll come back and reference this picture a bunch. Okay, so let me give you the definition, and this definition is a bit of a bear. It's really long. A lot of parts going into it. Okay, so if f is some function, and it's the one that we're interested in, defined at least on the interval from a to b, so if f is a function defined on the interval from a up to b, then what we do, if I can write here, then we'll divide that interval a, b into n equally wide smaller intervals. So n equal intervals each with a width of the following. We did this last time. So we called the width delta x, and we found that delta x by doing b minus a, which is the total length of the interval from the right side down to the left side. And we chop that up into n equal pieces. So that's how big our delta x is. What we're going to do is we're going to label the endpoints of all of those little rectangles as follows. So we're going to let x0 be the starting point, the left end of our first interval, so it's going to start at a, and then x1 be the next point, so it's a plus 1 delta x in, and then x2 will be a plus 2 more delta x's, so we're 2 points over, and so on and so forth all the way up to x sub n. In this case, we've chopped it up into n different points, and that last one, x sub n, is going to be at the right endpoint, b. So these are all the endpoints, so let me erase that period. Let that list of points be all the endpoints of our n intervals that we've created. So we've created all these little tiny intervals. Here's all their endpoints. We've just listed them off. There we go. In addition, what we're going to do is we're going to let a bunch of points, x1 star and x2 star, all the way up to xn star. These are going to be points somewhere in those intervals. We're going to call them sampling points. So these are going to be the sample points in each interval. So each interval gets one sample point. Meaning that this first sample point here needs to occur between the first two. Here's the two endpoints of the first interval, right? So x0, that's going to be this point over here. x1, that's going to be this point right here. I'll draw them in colors in just a minute. And this number, x1 star, needs to be somewhere in between them. So it's a sample point somewhere in that interval. So there's sample points in each interval. So what I mean by that is that the ith one of these things, so the ith little sample point, will occur somewhere between x sub I minus 1 and x sub I. So checking our indexes using this index notation, if I want the first one, x1 star, this first point, x1 star needs to occur between x1 minus 1 is 0, so x0 and x1. Here's going to be x0, here's going to be x1. x1 star is a point in between them. That's all this is saying. Okay, so we've got our endpoints, we've got our sampling points. I'll come back and highlight them all in the picture in just a minute. But let's continue on with our definition. If all of this is true, then the definite integral, the thing that we're trying to define here, so the definite integral of f from a to b, so this is the wording that we'll use. We'll talk about a definite integral of some function f from a to b, from some starting point to some ending point. And it is the following. The notation that we're going to use starts off with a symbol that looks like this. It's like a really stretched out, vertically stretched out letter S. It'll have A at the bottom and B at the top to indicate where we are starting and stopping our definite integral. And then we'll specify which function we're computing the definite integral of. And lastly, it'll have this little symbol dx, a differential that we've talked about in the past. We'll come back to that as well. So this whole piece is going to be equal to the limit as n goes to infinity. So it's going to be equal to the area under the curve. And we did this last time. The area under this curve up here, give myself a little room so we can see maybe everything at once. Oh, come on. Too little. Okay. We're trying to find the area of that region. We said all we need to do is let the number of rectangles that we use here go to infinity. And so that's what we're doing. We're letting n go to infinity. And then we'll just take the sum. I'm going to have to zoom in to write clearly here. Let me try to do this again. Okay. So the sum from I equals 1 up to n of the heights, so f evaluated at the point x sub I star times the width, which is delta x. So this is the area of each little rectangle. We're adding them all up and taking the limit as the number of rectangles goes to infinity. So this is our symbol. So that's what that definite integral is going to look like, provided that that limit actually exists. So this is true provided the limit exists and furthermore that it gives the same value regardless of our choice of xi. So regardless where we pick that sampling point. And we'll talk about this again in just a minute in our picture. So if all of this is true, then we say that the function f is integral. There's another term that's important. Let me underline all the important terms that we need. Definite integral. That's good. Okay, so here's our giant definition. Let's just relate it to the picture, make sure that everything's totally clear. So let me now zoom out so we can kind of see everything all at once. Okay, so let's go through this definition more carefully. F is a function defined on the interval from a to b. Certainly the one that we've drawn is defined between a and b. It looks like it's also defined outside of that interval, but that's unimportant. All we care about is that it's at least defined from a up to b. we've divided that interval AB up into n equal parts. In this case, it looks like we made 8 of them. And we're listing off right here all of the endpoints of each of those intervals. So what I'm saying is these numbers, the x0, x1, x2, all the way up to xn, those are just these points. There's the first one, x0. There's x1, x2, x3, x4, x5, x6, x7, and x8, 8 being n, the number of rectangles that we made here. So those are all of the endpoints underlined in red. The sample points just need to be points anywhere in that interval. So these points are our sample points, x1, x2, and so on up to xn. x1 is somewhere in that first rectangle. And it doesn't matter where. It could be closer to the left, closer to the right side of that. It doesn't matter. x2, maybe x2 is really close to the left side. And maybe x3 is really close to the right side. It doesn't really matter. All that matters is that these sample points fall, there's one in each rectangle. And the sample points, according to our definition down here, they're going to be the points that we evaluate our function f at. So this is where we're getting our heights. These are the heights that we're trying to find. And so all I need to do is evaluate what the height of the function is at that particular x value. And that's what gives me the height of the rectangle. And maybe this one we evaluated, it's over here on the left. And that's how we got this particular height. And this one way over here on the right, it gave us this particular height. The whole point is we just need that point somewhere in there. It doesn't matter where it is, because what we're going to do is take the limit as the number of these rectangles goes to infinity. And as the number of rectangles goes to infinity, what happens to the width of them? Well, here's our width, delta x. As n goes to infinity, we're taking a finite number, dividing it by infinity. Our width is going to 0. And so basically what it's saying is these endpoints, all the red points that I've drawn here, as we get more and more rectangles, those endpoints are going to squeeze together. This first interval is going to become something that has a width of 0. That x1 is going to go and approach x0. And this point is just forced to stay in between them. That's by definition what these sampling points need to be. They need to be somewhere in that interval. So it doesn't really matter. Eventually it's going to shrink down to there's only one point for it to be able to fit anyways, as we shrink the two red points together. So as the two red points squeeze together, the blue point just needs to stay in between them, and it gets squeezed down to a single point. So we don't really care if it starts on the left or starts on the right. At the end of the day, it just needs to be between those points. So this is our definition of a definite integral. We talked about this last time. We even started a problem. We left the problem as it was because we needed a computer. So this was like sort of the last example we did was something like this. And what I'm telling you now is this is how we're defining our definite integral. We're defining the definite integral via the same process that we use to find the area under the curve. And that's why we can interpret the definite integral as the area under a curve. I mentioned this, I warned you about this last time. That is only one interpretation. We will see other interpretations of the integral later on. So there's a lot of things to unpack here. So let me go through a whole bunch of kind of important side notes. So I'm going to label them all here. They're all kind of important. So let's number them. Here's note number 1. And this has to do with notation. Notation that we're using. This symbol, this thing is what we're going to call an integral sign. So maybe I should not use an equal sign there. Let's just use an arrow. This thing is an equal sign. Or sorry, this thing is an integral sign. The history of it, the reason it looks like a big stretched out letter S is because that's originally what it was meant to be, a big letter S for the word sum, because we were summing everything. But we now just refer to this shape as an integral sign. You'll see it a bunch in the textbook. The A and the B that showed up in our notation over here, the A and the B here, those are our lower and upper limits of integration. So that's lower slash upper limits of integration. That's how we refer to where we start and stop our integration. There, the lower limit is where we start, the upper limit is where we stop. The f of x, the function that we're using, the word that this will be referred to as is the integrand. It's the thing that gets integrated. And the dx, we've seen that before, this is a differential. And it's going to be important. We can't leave the differential off. So this is what each individual piece that goes into this notation, what it means, the word that we're going to use for it. If you hear the word integrand, that just means whatever's getting integrated. So there's our first note. Let's do some additional notes. What else do I need to say? Oh, this is an important idea. Note number 2. Our definite integral that looks like this, it's a number. Right? That number is whatever the area happened to be. There's not going to be any dependent on x. There's an x in the original notation, so we have this x here. Got x showing up in there. Let me stick with the black marker here. So there's no dependence on x in the final answer. It's just a number. So viable answer, when you actually later down the line compute one of these things, 3. That's an okay answer. 2.74375, that's a viable answer. Pi, that's a viable answer. But e to the x or 2x minus 5, those are not viable answers. They still involve x's. There will not be an x in the answer for one of these definite integrals. It's an area, and it's just going to be a number. When we relax the restriction, and we'll do this in the next section, of not having a starting and stopping point and moving to what we call sort of an indefinite integral, that will have x in the answer. But for these, if you have an a and a b here, a starting point and a stopping point that tells us where we're finding the area, you should just get a number from this thing. One thing that means is I don't need to use x here. I could replace this with any other symbol, and the answer would be the same. I want to use a t, that's fine. I want to use a y, and s, smiley face, Batman symbol, doesn't matter. The variable name doesn't matter. This is just going to spit out a number regardless of what symbol we use in place of the x. Okay, another note. So far we've only looked at pictures, so note 3, we've only looked at pictures where f of x was positive, meaning it existed entirely above the x-axis. So what if f of x has negative portions? So meaning, let me draw a picture of what I mean. What if this is the picture we're dealing with? What if our function goes like this? Maybe here's a and here's b. And here is our y equals f of x. There's x and y. Well, we have a region where it's positive, another region where it's positive, and then we have this region where it's negative in the middle. Negative regions will contribute, as weird as this sounds, negative area. So let me put that in quotes because there's no such thing as negative area. But we can think of it as sort of a signed area. These will be positive contributions to our overall number. This will be a negative contribution to the overall number. So this thing's going to spit out just a number, as we just said. These parts will give positive contributions, this will give a negative contribution, and depending on how those balance out, that'll determine what our final number winds up being. So we call this the total result that takes into account both pieces is called the net area. So if you're asked for the net area, that's what they're looking for, the positive parts minus the negative parts. One other thing worth mentioning, at the very end of our definition we had this term integral. We said that, here we go, provided that this limit exists and gives the same value regardless of the choice of xi, that means that our function f is integrable. Pretty much all the functions that we're used to dealing with on a regular basis are integrable. So this is note number 4. So most normal functions, in fact all the normal functions that we're used to, but we will have to treat certain points kind of carefully. So if it has jump discontinuities, so even jump discontinuities, where the function jumps from one value to another, where you're doing something like, let me just do this on this side and I'll delete it, where you're going along this way and then all of a sudden it jumps up to here and then keeps going that way. That's allowed. That's not a problem. We can have that type of a shape. So even jump discontinuities are integrable. We can't compute the derivative at a jump, but we can still compute the integral through one of those. So as long as we have a finite number of these types of discontinuities, we're going to be okay. The only question that we're really going to have to worry about is what happens if we're trying to integrate and we go across some sort of, maybe this is what our axis looks like, and we go across, here's where A is, B is over here, I don't know why I drew it on the bottom, let's draw it on the top, B is on the top. As well, and we've got to take into account these negative contributions, then we've got a positive contribution, then all of a sudden we've got this negative contribution, and we have this weird asymptote where things jump. That's going to require a little bit of special care, but for the most part, the functions that we're used to dealing with, we're not going to have to worry about this stuff. So let me just delete that little picture. Okay, so I think we knocked out all of the notes. Hopefully the conceptual ideas are starting to come into play, but to get comfortable with these things, we need to do some examples. So let's jump to some examples. So let's look at an example here first. Let's see if we can find the integral from 0 to 2 of the square root of 4 minus x squared dx. And we want to find this by treating it as an area. So this is the idea. It's really important to keep in mind we can treat these things as areas. So let's draw this particular function. Here is my set of axes. So here's my x and y axes. And this shape is an interesting shape. Let me just write it over here. If I'm trying to graph y equals the square root of 4 minus x squared, you may not recognize it offhand the way that it's written, But if I rearrange things, so I'm going to take this equation and just algebraically manipulate it a little bit. First thing, I'm going to get rid of that square root. So I'm going to square both sides, and I'll get y squared equals 4 minus x squared. And then I'm going to move that x squared over to the same side as the y squared. So I'll have x squared plus y squared equals 4. This is hopefully something you do recognize. That's a circle with the radius equal to 2. And so it's centered at the origin, goes up to a height of 2 here, goes over to point 2 over there. This is the shape that we're dealing with. It's a quarter of a circle in this case because we're going from 0 to 2. So I want to find the area of that region. Notice we're using the version with the positive square root. That means we only have the upper half of the circle. If there was a negative square root, that would allow us to draw the bottom half of the circle. But again, a circle is not actually a function because otherwise it would be multi-valued. It wouldn't pass the vertical line test. So the positive square root gives us the top half. The negative square root gives us the bottom half. In this case, we're dealing with a positive square root version. So this is the picture. I just want to find that area. So all we need to do then to find the answer to that integral is we want the area. So what is the area of, in this case, that's a quarter of a circle with a radius equal to 2. So that's all we need to find. So that area is going to be a 1/4 of the normal area of a circle, which is pi r squared. But in this case, r is equal to 2, so we're going to get 1/4 of pi times 2 squared. 2 squared is 4. I'm going to get a 1/4 of 4 pi, which is just pi. So there's our answer. So what we found is we know that in this particular case, the integral from 0 to 2 of the square root of 4 minus x squared dx is going to be pi. And we know that by treating it like an area, drawing the picture, treating it like an area. Okay, so most of the time we're not going to get lucky and wind up with a function that is basically a nice geometric shape that we know the area of anyways. We're going to need a different approach. So in our next example, let's try to treat this thing as though it were a Riemann sums. Essentially, let's use this limit definition. And we're going to need to know a couple of things that I will point out along the way. But for now, let me just write out what we're going to do. So I want to convert the integral from 0 to 2 again of a different function. Let's do a quadratic. X squared minus 2x plus 1 dx. And oftentimes, to make it clear, sometimes some people will throw parentheses around there to make it clear that we're taking the integral of this entire thing. I'm fine with you leaving off the parentheses. It's kind of pretty clear that the whole thing is what we're interested in. But I want to convert this to a Riemann sum. And all I mean by a Riemann sum is this thingy. So the normal sum, that little spiky backwards E looking thing, or backwards 3, I guess, looking thing. And then actually compute the answer, so find the value by actually evaluating the limit. So this is the way that when calculus was first invented, this is the way that it was approached. Exactly how we're going to be doing this. So, I need a few different things. I need to figure out, so our goal is to find essentially, again, the area under this shape, and it's the limit as n goes to infinity of the sum from I equals 1 up to n of f of xi star delta x. This is the limit that I'm talking about. This is our limit definition of one of these things. So we need a few separate pieces here. The first piece I want to know is, what is delta x? Well, in this case, our interval is a length of 2. We're integrating from 0 up to 2. So our definite integral starts at 0, goes up to 2. So that's the total distance, and we're trying to divide it up now into n total rectangles. So the width of each one of those little rectangles is going to be the total distance, which is 2, divided by n, the number of rectangles. So this is simple. This is just 2 over n. There's our delta x. The next thing I want to figure out is, where are these xi stars occurring? We already saw that it really doesn't matter where we put them, so let's just put them somewhere convenient. I'm going to put mine at maybe, I don't know, all of the right endpoints of the graph. So again, we're starting at 0, so xi is going to be 0 is our starting point, and we'll just say plus delta x maybe times I. So let me do that in the reverse order. So plus I delta x. So where did I come up with this? Let me draw our picture over here. This thing is a quadratic. Hypothetically, let's just forget, let's pretend I have no idea what it looks like. We can graph it in a little bit, but who cares? Something like this. And I'm interested in going from 0 up to some point over here, 2. So it looks something like this, whatever. I want to know, as I chop this thing up into my rectangles, I'm suggesting maybe I can just use this point, this point, this point, all the right endpoints to be the points that I'm interested in. So right here, this first one, this needs to be my x1 star. And this second one right here should be my x2 star, and so on. We'll just use all those right endpoints. So what is this location right here? Well, it's 0 plus 1 delta x. So 0 plus, when I is 1 and I'm looking for x1, it'll be plus 1 delta x. And that would put me right there. And if I wanted to get x2 star, that'll be 0, my starting point, plus 2 delta x's to get me to this point. 3 delta x's to get me here, 4, and so on, all the way up till the last one, albeit n delta x's will get me to the last point that I'm interested in. So 0, this is sort of the starting point. This is our lower bound of integration, and this is just keeping track of how many delta x's do we have to move over to get to that point. So that's kind of what's going into the formula. That's how I'm thinking about this. So with this in mind, if I actually clean this up, we just found what delta x is. It's 2 over n. So I can rewrite this whole thing as just 2I over n. Again, the delta x is the 2 over n. The 0 I can ignore. Our starting point was just 0 anyways, so I don't need to add explicitly 0 plus this. And the I just gets carried through. So when I is 1, I'll be at the point 2 over n. That's right here. When I is 2, I'll be at the point 4 over n. And that happens to be right here. And so on and so forth. Will get us all of those endpoints that we're looking for. So I have an expression for delta x, I have an expression for my xi stars, my sampling points, and now I can rewrite my entire thing in terms of these. So we can write, so we get the following. Our limit for our area, which is the same as that integral that we're looking for, is the limit as n goes to infinity of the sum from I equals 1 to n of the following. I just need to evaluate f of x sub I star. And here's my x sub I star right here. So I want to do f of that. So my f, just to zoom out so we can see everything at once, do not want that. There we go. Here's the f that I'm using. It's x squared minus 2x plus 1. And here's the input, my xi star that I'm plugging in. So I need to, for the first term, take this piece and square it. Then the next term will be minus 2 of this. And then lastly, it'll be a plus 1. So I'm going to get 2i over n quantity squared minus 2 times this 2i over n. And lastly, plus 1. So there's the whole thing. Now I need to multiply that by my delta x, and my delta x is just 2 over n. So here's where I get an extra factor of 2 over n. So let's just color code these things. This is the same as this piece. It's my delta x. And this whole thing is the same as this whole thing. I'm just evaluating the function, plugging that in for what the x sub I star is. So that's the idea. So all I've done is fill out our generic limit up here with the specific values for this particular function. Okay, so our goal is to somehow evaluate this. And to do that, we need to know a few special rules. So this is sort of a side note. So I'll call them tricks. I don't like to talk about tricks in math classes, but really these are outside the scope of calculus. These are things that are done often in like a combinatorics class. These things come up in statistics. Essentially, here are these tricks. Whatever, we'll use the word rules. Maybe rules sounds more formal. But here's the idea. If I am summing from I equals 1 up to n, something that just involves I. So I'm just summing the number I from 1 to n. Basically, imagine n was 100. All this is saying is I want to add every number from 1 up to 100. This was something that Gauss, the famous mathematician, also physicist, if you've taken any physics and you've heard of like Gauss's law or anything like that related to electromagnetism, if you've ever heard of the idea of degaussing something magnetic, all named after the same dude, he did this when he was like 5 or 6 years old. His teacher gave him basically this tedious thing to pass time and said, add up all the numbers from 1 to 100. And he did it in like 30 seconds. Let me give you the formula. He's the one that basically invented this formula, and I'll tell you exactly what went into it. There's the formula. So it turns out that is the number that you would get. So if you want n to be 100, I want to add the numbers from 1 up to 100. I'd just plug in 100 here. So it'd be 100 times 101. Get that result, divide it by 2. That's the sum of all the numbers from 100 to 101. Where does this come from? Essentially, it comes from the following. If you list all the numbers, so let me just do it really long ways here. So 49, 50, 51, 52, dot, 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 dot. Let's just say 96, 97, 90. I guess I didn't need the 96. Let's do 97, 98, 99, and 100. Here's all the numbers, and we're adding them up. Instead of adding them up in order from left to right, what I'm going to do is pair them. So I'm going to pair this one. In fact, let me make that a little bigger. I'm going to pair this one with this one. I'm going to add those two together. And similarly, I'm going to add this one with its partner, this one, and this one with this one, and so on and so forth. So I'm pairing them up, working from both ends inward, And when we get to the very middle, it'll be these ones that get paired up. And if you notice, each one of these pairs, so the first one is the number 1 plus 100, it sums to 101. And the next number is 2 plus 99, and it also sums to 101. And then the 3 plus the 98 sums to 101. And 4 plus 97 sums to 101. 49 plus 52 is 101. 50 plus 51 is 101. We've got all of these pairings. They all add up to the same 101. This is essentially n plus 1. One more than the number that we set out to compute our sum up to. How many of these pairs do we have? Well, if I just count one side of each of the pairings, so let me just count the left-hand sides here. It's this one, this one, this one, this one, all the way up to this one. This is our last pairing. After that, I'd be going to all the right numbers. So up to this point, I can cut it off right here. How many total pairs do I have? Well, I have 50 of them. There's 50 total pairs. I started at 1, added up to 50, and after that, I'm moving on to the right, the larger number of in the pairings, the right number. So there's 50 total. So we have 50 total pairings. Where does that 50 come from? That number is just n divided by 2. And that's what gives us our formula. We've got 50 pairs times where each one is a value of 101, so I just need to multiply the 50 times the 101. That's exactly what this thing is right here. It's n over 2. There's the 50 times the n plus 1. We've just rewritten it a little bit different way. So that's where this formula comes from. We now have a quick, easy formula if we want to compute the sum of a bunch of numbers from 1 up to n. I can compute the sum of just that number. There are some similar formulas that I'm not going to give you an intuitive explanation where they come from, but it's similar, that look like the following. So what if instead of adding up all of the numbers themselves, what if I want to add up every single number squared? Well, it turns out the formula for this looks like n times n plus 1 times 2n plus 1, whole thing divided by 6. And the last one, what if instead of adding up each number or each number squared, what if I want to add up each number cubed? So the cube of each number. In that case, you wind up getting something that looks like this. It's n times n plus 1 over 2, whole thing squared. So these are going to be some formulas that we're going to be using to evaluate this ugly mess that we've come up with right here. So n is just a constant, right? It's the thing that we're eventually taking the limit of, but it's not affected by this sum. We're summing over the i's. Anything that an I shows up, that's where the sum is occurring. N, as far as we're concerned, we can pull n outside of this sum. So let's take a look at some other things. One other thing I should mention, I guess, let me add this to the list of rules. Maybe that's a better way to do it. So let me add a couple extra rules in here. What if I want to add up from I equals 1 to n, just some constant? So something that has no dependence on I. I'm just adding up a constant n times. So 3 plus 3 plus 3 plus 3 plus 3, and I'm doing it 20 times. Well, that's just 20 times 3. So in this case, it would just be n times c. So there's one thing you can do. Some other rules, just how to manipulate these things. If you've got the sum from I equals 1 up to n, and you've got some constant times something that does depend on I. So ai could be any one of these things that we have up here, any other thing that happens to depend on I. The point is that constant, as far as the I is concerned, it doesn't have any I dependence. I can pull it outside of the sum. So I equals 1 to n of just the ai. And similarly, just a couple other quick rules. If you are taking the sum from I equals 1 to n and you've got an AI, something that depends on I, plus or minus a second thing that also depends on I. Well, it turns out you can split that up into two separate sums. So I could write that as the sum from I equals 1 to n of the A term, plus or minus the sum from I equals 1 to n of the B term. So you can split these things up. So here are now all of my rules, just so we can manipulate these things. And we're going to apply all of these rules now to this example right here. So let's try to do that. So we get, when it's all said and done, first things first, I've got my limit as n goes to infinity. I don't want to forget that limit. We'll evaluate it at the very end. But we had a 2 over n that was at the end. I'm going to pull it to the front outside. So this blue piece right here, I can pull it all the way outside the sum because, again, as far as this is concerned, it has no dependence on I. You can pull it outside the sum. I'm basically utilizing this rule right down here. I'm pulling this constant 2 over n outside of the sum. So it's going to be outside the sum, and then we have the sum from I equals 1 to n of all of those remaining terms. So let me write them all out. The first one we had was the 2i over n squared term. Then we had, was it plus or minus? I think it was minus. Minus 2 times 2i over n. And then lastly, plus 1. So this is what we've got right now. So all I've done so far is I pulled this piece outside of the sum. Next thing I'm going to do is just algebraically manipulate a little bit of stuff, move some stuff around. I'm going to pull the parts of these that have a dependence on I. I'm going to separate them from the parts that have no dependence on I. So I'm going to rewrite this term, that first term, as basically the 2 over n squared part separate from the I squared part. And in the second one, I'm going to do the same thing. I'm going to have 2 times 2 over n, and that's going to be separate from the I part. And then lastly, we have a plus 1. So I've just pulled the i's out. So they are separate. And we can kind of now follow down through our rules a little bit more. This piece, I'm going to have my 2 over n. Let's break it up into a bunch of separate sums using this bottom rule that we have right here. I've got a sum of 3 separate terms. I can break that into 3 separate sums. So let's do that. And I'm going to kind of use a couple rules at once. This one, this part has no dependence on I, so I'm going to pull that outside the sum. So I can rewrite this first one. Again, there's that big 2 over n. But I'm going to pull out this 2 squared over n. That's 4 over n squared times the sum from I equals 1 to n of I squared. And for the second one, I'm going to have minus 4 over n times the sum from I equals 1 to n of just I. And for the last one, I have the sum from I equals 1 to n of just the number 1. Okay, so just to make it totally clear, the 2 over n is the same as this 2 over n. I haven't changed that. This piece right here, the 2 over n squared, I pulled that outside the sum, and I changed the 2 squared to this 4, and the n squared to n squared. So here's 4 over n squared, that's this piece right here, and I pulled it outside the sum. All I'm left with is the sum of the I squared part. Did the same thing here, converted this to 4 over n, pulled it outside of the sum. So here's my 4 over n outside of the sum, and all I'm left with is the sum of I. And lastly, here's one where we're just summing up the constant 1. So now we'll go up and use all of those rules. We're going to be using this one for the constant, the 1. We'll use this one for this I squared term down here, and we'll use the last one, the middle one rather, we'll use this top term here. So I'm going to replace it with all those pieces. So hopefully you can see them. I'll zoom out once we're done with this. So again, I haven't touched this limit yet. No, this is looking scary. Don't worry, you're not going to need to do a ton of these types of problems. We've got my 2 over n, and this first term is 4 over n squared. And the sum of the I squared terms, that wound up being, and this is just copied from one of those rules above, this was n times n plus 1 times 2n plus 1, the whole thing over 6. So there's the first piece. The next one is going to be minus 4 over n, and the sum of I, that was n times n plus 1 divided by 2. And the last one, when you sum up a constant, is just n times that constant. So in this case, n times 1 is just n. So there is a giant disaster of a mess. We can simplify a little bit. Every single one of these terms has at least an n in the numerator. We've got an n in the denominator out here. Let me cancel all of those. So I'm going to cancel that with that, and that, and that. And this is now just a 1. Okay, so let's distribute through this 2, see what we can do to kind of simplify things here. Again, we still haven't touched this limit. It's hanging around. We still have to do that. So I'm going to do this first piece. I'm just going to focus on this piece for right now. Okay, when I multiply that by 2, I'm going to get an 8 in the numerator, a 6 in the denominator. I can write that as 8/6. I will have an n plus 1 in the numerator and a 2n plus 1 in the numerator, and I will wind up with an n squared in the denominator. So that's that first term. The next term, I can cancel this 2 and this 4 to just get a 2 out of there. I'm going to get a 4, and I'm left with an n plus 1 in the numerator and an n in the denominator. So that is, this piece goes with this piece, and this piece over here was the piece that matched up with the other blue piece. And lastly, when I multiply the 2 through to this 1 over here, I'm just going to get plus 2 out of this whole thing. So this is the giant limit that I'm trying to take. Notice I is all the way gone. We lost that back a couple steps ago. We just got a big, ugly, ugly mess of stuff. So let's clean this up with a little bit of algebra and then actually finally take this limit. So one more step before we take the limit. So limit as n goes to infinity. This first piece, let me simplify that 8/6 to 4/3. And I'm going to kind of FOIL out that binomial there. I'm going to get a 2n squared. I will get plus n plus another 2n, so plus 3n plus 1 over n squared. So there's the first term. The second one is ready to go. It's just 4 times n plus 1 over n, and the last one is plus 2. So this is the thing I'm taking the limit of, this big ugly mess. So let's take this limit. What we get out of this piece that we're now finally attaching this limit to, so these should all be equals all the way down. These are all equivalent. My big old chain of equal signs that I forgot. We're good. What do we get? So what do we get for the limit of just this first piece? Again, we're taking the limit as n goes to infinity. The biggest power on top is n squared. The biggest power on the bottom is also n squared. As n goes to infinity, all I need to care about is the ratio of these two coefficients. These other terms are going to be much smaller in comparison to the n squared terms, so I can ignore them. This is effectively just going to go to 2. So that piece is going to be the 4/3 times 2. The second piece will be minus 4. And as I take the limit of these, again, the highest power on the top is n to the first, same on the bottom, n to the first. the ratio of those two things is just going to be 1. So 4 times 1. And then lastly, the limit of 2 as n goes to infinity. Well, there is no n, so it doesn't affect the constant. It's just plus 2. So at the end of the day, the thing that we're going to get out of all of this is a big, ugly number here. This thing is going to be, what? So 8/3 minus 4 plus 2. So just 8/3 minus 2, which I could write as 6/3. So this whole thing goes to 2/3. There is our answer. Our answer to this problem, as I promised, is just a single number. We started this problem way back there. There's this problem. This is what we just found. Let's write this down. Again, this will be useful. You might want to write these down separately somewhere for the homework. I think I only make you do maybe like one of these types of problems, maybe 1 or 2. It's not something you need to worry about a ton. If I put it on the final exam, I guess it won't be that big of a deal because now our final exam is going to be take-home, so maybe I will put it on the final exam. We'll see. But otherwise, we're going to have a much more efficient way to deal with these problems soon. So for now, what we've found at the end of the day is the following. All we did, there we go. We found that the integral from 0 to 2 of our x squared minus 2x plus 1 dx wound up being equal to 2/3. That is our answer. Okay, so there's some other problems that kind of involve the same type of thing. I'm going to skip some for now. There's some in the notes. But let me skip this page. This video is already getting super long. Let's just do one more example to kind of tie into this. And then we'll get a ton of examples starting in the next section. We'll do a bunch of examples in 5.3. Okay. So one thing that I want to note is that we can also use antiderivatives. I don't know why I'm hyphenating that. Antiderivatives. This is going to be the method that we'll use going forward. So we've done it the long way, but I want to show you that we can get that same answer in a little bit easier method going forward. So I mentioned this idea of an antiderivative is the same thing as an integral. And this is actually what we're going to look at in the next couple of sections. We're going to look at something called the fundamental theorem of calculus. And it basically ties together the idea of integration and differentiation as inverse operations, as things that undo one another. And so that's kind of what we're going to be looking at. We can use the idea of an antiderivative to mean the same thing as an integral, and that's kind of going to be our starting point. So let's look at the same example, but from a different approach. So again, I'm just wanting to do the integral from 0 to 2 of x squared minus 2x plus 1 dx. If we treat these integrals as antiderivatives, I can break this up into separate pieces. So I'm going to do the integral from 0 to 2 of x squared dx. Right? Remember that this is in parentheses. So you can think of that dx as kind of distributing through and hitting all of the separate terms. So I'm going to break it into 3 separate little definite integrals here. The second definite integral will be the one from 0 to 2 of negative 2x dx. And the last one will be the integral from 0 to 2 of just the 1 times the dx. So I've broken this single integral where the integrand has three separate terms, and I've broken it into three separate integrals where now each integrand is just one of the original three terms. Turns out that's going to be a rule that we're going to be allowed to do. And it has to do with, again, this thing is ultimately just a limit, so it follows the same limit laws that derivatives followed. Okay, so now I want to think of this symbol as antiderivative. And see what we get. So for this first one, I want to think of this piece right here. I want to find the antiderivative of x squared. The antiderivative of x squared is going to be x cubed with some coefficient out in front. And when I take the derivative of x cubed, I won't get x squared, I would get 3x squared. I don't want that 3, so how do I make up for it? Well, I'll put a factor of a third out in front of this thing. So that is the antiderivative of the x squared, and I'm going to put a symbol that looks like this with my 0 and my 2 to remind me that I need to now evaluate this function at those two different points. And again, this is going to be something we'll formalize in the next couple of sections. The next one I need to add, so this other one, I want to figure out what is the antiderivative of this piece. So forget about the negative 2, it's just sitting out in front. What is the antiderivative of just the x? So the x, I know it'll be x squared, but when I take the derivative of x squared, I will get 2x, not x, and I don't want that 2x, so I'll put a 1/2 to make up for it. And we'll be able to cancel that with the negative 2 in just a minute. And again, that thing's going to be evaluated between 0 and 2. And lastly, the 1, what is the function that gives 1 as its derivative? That piece is just going to be x, evaluated between 0 and 2. The derivative of x is 1. So there are what those pieces look like. And lastly, don't forget we have a plus c. And so this plus c, again, really we're thinking of evaluating it between 0 and 2, and we'll touch on this in just a minute. So that straight line means evaluated at, and what it means is I need to take each one of these functions and evaluate them at the 2 on top, and then also evaluate them on the 0 at the bottom and take their difference. So this is what the notation is going to be. When you see this notation, means evaluated. Maybe a better way to phrase it is to say evaluated between those 2 points. So that's kind of what this notation means. So what I'm going to do is take my 1/3 x cubed, and I'm going to evaluate it at 2. So it's going to be 1/3 times 2 cubed. And I'm going to do all of the upper bounds together. This next one will cancel this with this. I'm going to get minus 2 squared. So that is just looking at this piece. I've canceled off the 2's. The minus is this minus, and I just plugged in a 2 for x. So it's 2 squared. This last one's going to be plus 2. And then I've got a plus c. It doesn't matter that it's at 2. It's a constant, so it's always c. So there's all of the upper bounds. That's evaluating everything at 2. Then I have to subtract the result that I get evaluating all of these at the lower bound. This is going to become a process that you'll get used to very shortly. We evaluate at the upper bound, we evaluate at the lower bound, and we take the result at the upper bound minus the result at the lower bound. We'll always do a minus right here. So at the lower bound, it's going to be 1/3 evaluated at 0 cubed minus 0 squared plus 0 plus c. So I did the same thing I did here with 2's, I just did it with all the zeros at the bottom. And what do we get out of this? Well, this number right here, 2 cubed is 8, that's going to be 8/3. And from that I'm going to subtract off 2 squared, that's minus 4. And then I need to add 2 and add c. Over here I'm then subtracting off this piece is a 0. This piece is also a 0. The minus signs would distribute through and I'd be adding a 0. Minus sign would distribute to this one, I'd be minus a 0. Minus sign distributes through all the way to the c, and we get minus c. So these are all, I don't care about the plus 0, minus 0, they're all zeros, it doesn't matter. But this piece I have a plus c, and this piece I have a minus c. They're going to cancel. And in general, this is always going to happen. So I don't even need to say in general. This is always going to happen. We don't even need to write the plus c term with our antiderivatives when we're doing one of these problems, as long as it is a definite integral where we've got these bounds, because we're always going to evaluate at the upper bound and the lower bound and take the difference. We'll have a c in both terms. I'll have a plus c in one. We'll subtract c in the other, and they will cancel. So we'll always have that. So at the end of the day, this answer is just going to be 8/3 minus 4 plus 2. That's the exact math that we just did, right? So what I've got right here is the same thing that we got right here. It's going to have the same simplification. This simplifies to 2/3. There's our final answer. So this is going to be eventually the way that we're going to treat these problems, using antiderivatives. But on this homework, you'll have 1 or 2 problems where you've got to do it this hard way. Okay, so I'll see you guys in the next video. I guess I won't actually see you. You'll hear me in the next video, and we'll go over the next section where we start to flesh out the results and details related to treating integrals as antiderivatives and finding that connection.